Hi everyone, my name is Billy. I'm delighted to get to talk to you today about some work I did last year, looking into this habitable zone Super-Earth LHS 1140b with the Hubble Space Telescope. So as many of you know, the Hubble Space Telescope is the only space-based facility that is currently operating and providing infrared spectroscopy. And here we're using the wide field camera 3. And the most widely used mode of this is to use the G141 grism. And this covers around 1.1 to 1.7 microns. And this is used to study a whole host of different exoplanet atmospheres. So essentially what happens here is that Hubble does this nice little wiggle to give you a spatial scan. So you have here in this image the spectral information in the x-axis, and in the y is the spatial, and so this spectral is put along the spatial axis to increase the exposure time and therefore the duty cycle and the SNR of your final observations. So we analyzed this data with the Oraculus pipelines that was used to reduce the data, produce the final spectrum, and then retrievals were done on this with the TARX3 retrieval suite. So I'll note that both of these codes are open source. I think you can pip install both of them. And so there's plenty of documentation and that sort of thing online as well, if you want to have your own go at trying to analyze this data set or others. So the planet we were looking at here is LHS 1140b. LHS 1140 is an M dwarf. This is true of, I guess, most of the studies we've currently done of sort of small temperate planets with HST and probably with James Webb as well, just simply because of the transit depth that you're getting. The relative radius ratio between planet and star makes these very favorable for atmospheric follow-up. LHS 1140b sits in the radius valley, so a radius of 1.7 Earth radii, but it has a very high mass, around 7 Earth masses, giving a density which is compatible with a silicate core. Due to its slightly longer orbital period, the planet orbits within the habitable zone of its star, so around 240 Kelvin is the equilibrium temperature. So in 2017, there were 2 Hubble observations that were taken of LHS 1140 as part of a program led by Jason Dittman. And so these are the extracted light curves using Oraculus shown here for the January and December visits. And the first thing that is kind of clearly obvious is these big spikes you see in 3 of the orbits for the January visit. And so our first question was, what's causing these, and can we correct for it, or can we still use this data? And when you look into it, so I've shown here 2 GIFs of all the data for both of those visits. So you can see the December one, there's essentially not much going on. It looks almost stationary. But in this January visit, there's a lot of different effects that are happening. So firstly, there's large shifts in the position of the spectrum on the detector. So in orbit 2, for example, this goes up to 12 pixels in the X direction and around 10 pixels in the Y direction. So there's large movement of the spectrum. So I tried removing these data that had shifted and see if we could still fit it, but because of this other degradation that you can see occurring throughout the visit, I think it might be due to South Atlantic anomaly passage or something like that. But essentially the data set from this January visit is just not usable. So that leaves us with the December visit, and that one fitted very nicely. And when we extracted the spectrum and then produced retrievals on it, what we found was that the signature we see is best fit by water. So we tried a number of different molecules, including methane and ammonia and carbon dioxide and so on. We tried these both individually and all together, but the only opacity source we could get any evidence for was for water. So this is assuming hydrogen helium dominated atmosphere. And the first kind of question you want to answer when you see a detection like this is what is the significance of that detection? And I think perhaps by looking at the data, you can see that it's not very good. And this is confirmed when you start comparing the model to a flat model, so a model without water to one with water. So we looked at the Bayesian evidence for both and converted that to a sigma detection, and that gives you around 2.65 sigma detection for water being present between these two models. But of course, you know, the whole point of the last few days and of this analysis group is the issue of stellar contamination, and this is something else that we all know can cause features in the transmission spectrum. So we tried to account for this as well. So we used the models from Rackham et al. 2018 and took the parameters for an M4 star, which was the best match for LHS 1140. And we computed, and I say we, I mean Miyoko Morai, computed 8 models. So there was 4 different spot types, which are shown there. So giant spots and solar spots, and then both of those with faculae as well. And then 2 different coverages, there's mean and max cases. So we had 8 different models of the stellar contamination, and then we saw, okay, what kind of signature would they produce over the WFC3 wavelength range? And so what we found is there's 3 different models that would cause a kind of feature around this 1.4 micron wavelength region, where you get this water feature as well. So they are the solar spots, which are shown in green. So the max case is the solid line. Okay, and the mean case is the dotted line. And so essentially, yeah, the best fit here was the solar spot model. But if we extend it to the visible, you get a lot larger features. And luckily, there was some data taken by Diamond Low et al., and there's also a test observation. So if you went into the visible, what we found there was that the solar spots with faculae could be the best fit model, but potentially the observations aren't compatible. You can get offsets between different instruments due to using different parameters or limb darkening coefficients or stellar variability and so on. So we wanted to check that that wasn't driving the reason for finding this as our best fit. So we forgot about the HST data for a minute and focused on the ground-based data, renormalized all these stellar models to these to see which one the best fit was, and essentially found that then your best fit model would change to the giant spots and faculae. So this has been, you know, considering each of these effects on their own. The next thing to do was to subtract each of these stellar models from the spectrum and then try fitting the retrievals again to see how, you know, would you still get water out? What we found with 5 of them, you still get water detection. For 2 of them, you don't. And for 3 of them, you don't, sorry. And for 2 of these, I've labeled it with WGB, which means weird ground-based. And so this is essentially, if you subtract this model off here, what you'd get is a very steep slope from going very low at 0.6 to very high at 1 micron. And this would be tens of scale heights in size, which is just, you know, you can't fit that with an atmospheric model. So essentially, there's only one model that would completely rule out the water detection. So what's needed next? I think, you know, this has been discussed a lot so far, and I'm just repeating what's already been said, but a higher quality transmission spectrum will help break degeneracies, both with the planet's parameters, but also with the star. Getting an understanding of the star is obviously massively important, and maybe, you know, fitting the stellar model within the retrieval, which was mentioned by Ryan yesterday, would be a good way of, a better way of approaching this than doing it as 2 separate exercises as we did here. So in conclusion, LHS is this temperate rocky world, very interesting, and the HST spectroscopy potentially shows evidence for water, but it's somewhat unconvincing. So we need James Webb to really probe these worlds, but if we're going to do that, then knowing the star is crucial for that. And thank you very much, and I'll take any questions.
Wonderful, thank you so much. If anyone has questions, please remember to put it in the Slido. So I'll start with a question from there, which is, do we have any, an anonymous question actually, do we have any a priori ideas of what the atmosphere of LHS 1140b might look like?
Yeah, so I deleted this slide because I didn't think I'd have time, but we looked into forcing secondary atmospheres because I think that's probably what is expected for LHS. So from the density, it's very unlikely that you'd have a large hydrogen helium envelope. But the Bayesian evidence was essentially the same for each of those fits. So the data was equally well fit by all those models. So we can't tell with the spectroscopy, but the RV and transit depth seems to show it would unlikely be a primary atmosphere.
Excellent, thank you. Okay, I think in that case, it is actually time for us to move on. So if people have additional questions, remember to go to the Slido. Thank you very much, Billy.